So, here's something worth thinking about as you settle in tonight. Feel the weight of your body on the bed. That weight is real. It is you, pressing down, held by the mattress. And nearly all of it, almost every ounce of you, lives in a place unimaginably small. Not in your skin, or your bones, or your blood exactly. In the tiny cores at the center of your atoms, in the protons and neutrons packed into those cores. Almost all of your mass is there, in specks far too small to picture. And here is the strange part, the part we are going to sit with tonight. Those specks are not what you think. A proton is not a small, calm, solid ball. It is not 3 quiet little marbles stuck together, the way the simple picture says. Look inside one, really inside, and you find something closer to a storm. A roaring, churning, furious place, full of countless fleeting particles, flickering in and out of being, bound together by a force so strong it defies imagination. Almost all of your weight, it turns out, is not made of stuff at all. It is made of the energy of that storm. You are mostly motion and binding and force, held in a shape you call a body. Tonight we are going to travel there, gently, all the way down into a single proton, and see the storm inside. You do not need to follow every step. You do not need to hold anything in your head. If you drift off somewhere along the way, that is completely fine. The storm inside your protons will keep raging while you sleep, quietly, holding you together, as it always has. The ideas will still be here in the morning, and so will you. So let's start where the story actually starts. Not inside a proton, but with the simple question of what anything is made of, because people have asked it for a very long time. Break something in half. Break the half in half. Keep going. Do the pieces get smaller forever? Or do you reach a bottom, a smallest piece that cannot be cut? The ancient Greeks argued about this. One of them, Democritus, guessed that there was a bottom, a smallest indivisible grain, and he called it the atom, from a word meaning uncuttable. He had no way to prove it. It was a guess, but it was a good one, and it waited more than 2,000 years for anyone to find out if it was true. By the early 1900s, we knew atoms were real, but we had also learned they were not the bottom after all. They had parts. We met the first of those parts on the night about electricity, the electron, pulled out of the atom by J.J. Thomson. So the atom was not uncuttable. It had pieces inside. And the question became, what is the rest of it? What is an atom actually shaped like on the inside? The answer came from one of the most beautiful experiments ever done, and it surprised everyone, including the man who did it. His name was Ernest Rutherford, a large, booming, energetic New Zealander working in England, one of the greatest experimenters who ever lived. Around 1909, he and his assistants set up a simple test. They took a very thin sheet of gold foil, hammered so thin it was nearly transparent, and they fired tiny, fast, positively charged particles at it and watched where they went. The expectation was gentle. The atom was thought to be a soft, spread-out thing, a kind of pudding of positive charge with the electrons dotted through it. So the little particles should sail straight through the foil, barely bending, like pebbles through fog. Most of them did. They passed straight through, as expected, but a few did something impossible. A few bounced back. They hit something in the foil and ricocheted, straight back the way they came. Rutherford said it was the most incredible thing that ever happened to him in his life. He said it was as if you had fired a large shell at a piece of tissue paper, and it had bounced back hand hit you. Something tiny and hard and dense was hiding in the atom, something that could turn a fast particle right around. The soft pudding was wrong. What Rutherford had found was the nucleus. The atom, he realized, is almost entirely empty space, with a tiny, dense, positively charged core at its center, and the electrons far, far out around it. Nearly all the mass and all the positive charge is packed into that minuscule core. We met this emptiness before, on the night about quark stars. If the atom were a great stadium, the nucleus would be a marble at the center. That is what the bouncing particles had struck. The marble. The rare few that came straight back were the ones that had scored a direct hit on that tiny, hard nucleus. Rutherford had found the heart of the atom, and it was almost unbelievably small. And inside that nucleus sit the protons, and, we later learned, the neutrons. It was Rutherford again who identified the proton, a few years later, as the nucleus of the simplest atom, hydrogen, and the positive building block of all the others. The name proton comes from a Greek word meaning first, because it was seen as the first and most basic piece of the nucleus. The neutron took longer to find, because it has no charge, and so it is hard to see. It hides. It was not until 1932 that a physicist named James Chadwick, working in Rutherford's laboratory, finally pinned it down. A particle almost exactly as heavy as the proton, but electrically neutral, sitting in the nucleus alongside the protons, adding weight without adding charge. With the neutron found, the basic plan of the atom was complete. A nucleus of protons and neutrons, wrapped in a cloud of electrons. The proton carries the positive charge. It was the next thing to understand. For a while, the picture seemed almost done. An atom was a tiny nucleus of protons and neutrons with electrons drifting around it. 3 particles, and you could build the whole world. The electron, the proton, the neutron. It was clean and simple and satisfying. And then, over the next few decades, it fell apart, because when physicists began smashing particles together harder and harder, they found that the proton and the neutron were not alone, and were not simple, and were not, it turned out, the bottom either. What happened next was a kind of chaos, and it is a lovely, slightly comic chapter in the story. In the middle of the 20th century, physicists built machines to accelerate particles and crash them together at higher and higher energies. And out of those crashes came new particles. Not just the familiar few, dozens of them, then more. Strange, short-lived things that flashed into being and vanished, each one a little different, each needing a name. The Greek alphabet was pressed into service. There were pions and cons and lambdas and sigmas, and a whole growing crowd of them. Physicists started, half joking, to call it the particle zoo. What was supposed to be a clean, simple world of a few building blocks had become a bewildering menagerie of dozens upon dozens of particles with no obvious order. One famous physicist, the great Enrico Fermi, is supposed to have grumbled that if he had known there would be so many particles, he would have become a botanist. Another said that the discoverer of yet another new particle deserved not a prize, but a fine. It was too much. The whole point of finding fundamental particles was to reach a small, simple set of building blocks, and instead, the list kept growing, with no end in sight, and no pattern anyone could see. Nature seemed to be mocking the very idea of simplicity. It was a mess, and messes in physics are usually a sign that something deeper is hiding underneath. When there are too many things, and no pattern, it usually means the things are not fundamental. It usually means they are made of something smaller, combined in different ways, the way all the millions of words in a language are made from a few dozen letters. Someone needed to find the letters. Someone needed to find the small set of pieces that could be combined to build the whole zoo. And in 1964, two physicists, working separately, did exactly that. One was Murray Gell-Mann, a famously brilliant and sharp-tongued American physicist who saw the pattern hiding in the zoo. The other was George Zweig, working independently, who found the same idea at nearly the same time. They proposed that all these dozens of particles were not fundamental at all. They were made of smaller pieces, a small handful of them, combined in different ways. Gell-Mann called these pieces quarks, a strange word he took from a line in a novel by James Joyce, 3 quarks for muster mark, and with just a few kinds of quark, combined in 2s and 3s, you could build the entire zoo. Every one of those dozens of particles was just a different combination of the same few quarks. The letters had been found. The order underneath the chaos was real. Here is how it worked, and it is beautifully simple. A proton, they said, is made of 3 quarks, 2 of a kind called up and 1 of a kind called down. A neutron is also 3 quarks, 2 down and 1 up. The other particles in the zoo were other combinations. Some were made of 3 quarks. Some were made of a quark and an antiquark, a quark and its mirror image partner, paired together. With a small alphabet of quarks, the whole sprawling zoo snapped into order, like scattered iron filings suddenly lining up in a field. It was a triumph. It brought sense to the chaos. And it said that the proton, that supposedly fundamental particle, was not fundamental after all. It had 3 pieces inside. But there was a problem, and it was a serious one. And for a while it made many physicists doubt that quarks were real things at all. Nobody could find one. If a proton is made of 3 quarks, then surely, if you hit it hard enough, you could knock one loose and catch it, and hold a single quark in your detector. But no matter how hard anyone smashed protons together, no lone quark ever came out. Not one, ever. The quarks refused to appear on their own. So many people treated the quark idea as a useful bookkeeping trick, a clever way to organize the zoo on paper, but not necessarily a claim that there were really 3 little objects rattling around inside a proton. To believe the quarks were real, you would have to actually see them in there. And that took a different kind of experiment, one that did to the proton exactly what Rutherford had done to the atom. It looked inside by throwing things at it, very hard, and watching how they bounced. That experiment was done at a long laboratory in California, at Stanford, at the end of the 1960s. It used a machine that accelerated electrons to enormous energies and fired them straight at protons. And the idea was exactly Rutherford's, only 1 level deeper. Rutherford fired particles at atoms and, from how they bounced, discovered the tiny hard nucleus inside. Now physicists fired electrons at protons and watched how they bounced, hoping to see whatever might be inside the proton. The technique is called deep inelastic scattering, which is a mouthful, but the meaning is simple. Deep, because the electrons probe deep inside, and it tells you whether the proton is smooth all the way through or whether it has lumps. And it had lumps. When the electrons came flying out, some of them had bounced hard, at sharp angles, exactly as if they had struck something small and hard inside the proton. Not a soft, smeared-out ball. Hard little points, scattered inside, that could knock an electron sideways. The proton had parts. Just as Rutherford's bouncing particles had revealed the nucleus inside the atom, these bouncing electrons revealed hard points inside the proton. The quarks were real after all. They were really in there, 3 little scattering centers, and now we had seen them, not directly, but by the way they turned the electrons aside. The physicists who led this work, Jerome Friedman, Henry Kendall, and Richard Taylor, later shared the Nobel Prize for it. The quark had gone from a bookkeeping trick to a real thing hiding inside every proton in your body. It is worth knowing that there turned out to be more kinds of quark than the two we have met. The proton and neutron need only two, the up and the down. But nature made 6 in all, in 3 pairs, each pair heavier than the last. After up and down come charm and strange heavier cousins, and heaviest of all come top and bottom. The lighter 4 were pinned down over years, but 2 moments stand out because they changed how sure everyone was that quarks are real. The first was in 1974, and physicists remember it as the November Revolution, which tells you how much it shook them. 2 teams on opposite coasts of America discovered the same new particle at almost the same moment and announced it within days of each other. It was a particle made of a charm quark bound to its antiquark, and it was so sharp and clear and long-lived that it could not be explained away. It was direct, undeniable evidence that the quark picture was correct, that these things were real objects that combined by real rules. After that November, the doubters mostly fell silent. The quark model was no longer a clever bookkeeping trick. It was the truth about matter. The last quark to be found was the top, and it hid for a long time because it is astonishingly heavy. A single top quark weighs about as much as an entire atom of gold, though it is a point with no size at all. It took until 1995 and one of the largest colliders in the world to finally make one and confirm it. With the top quark, the family was complete. 6 quarks in 3 pairs. But only the 2 lightest, the up and the down, make up the ordinary matter of the world, the protons and neutrons of every atom, of every star, of you. The others are heavier, rarer, quick to decay, glimpsed mostly in colliders and in the fury of the early universe. You are built, at bottom, from just the 2 lightest quarks there are, the humblest members of the family, up and down, 3 to a bundle, in every proton and neutron of you. There is a lovely footnote to how we first made sense of those bouncing electrons, and it involves Richard Feynman, one of the most beloved physicists of the century. When the deep scattering results came in, showing hard points inside the proton, Feynman did not, at first, call them quarks. He was cautious. He simply called the little points inside the proton partons, meaning parts, the parts of the proton, without committing to what they were. It was a careful, humble word, and it let him work out the mathematics of how the electrons scattered off these parts, whatever they turned out to be. Over the following years, it became clear that Feynman's partons and Gell-Mann's quarks were the same thing, seen from 2 directions, and that the sea of gluons was in there too. But the word parton stuck around, and physicists still use it, fondly, when they talk about the whole churning crowd inside a proton, the quarks and the gluons together, all the little parts of the storm. It is a reminder that good science often starts by naming what you see plainly, and only later learning what it is. So the simple picture seemed confirmed. A proton is 3 quarks, 2 up, 1 down. Small, hard, real, sitting inside. And if that were the whole story, it would be tidy and lovely, and this would be a short night. But it is not the whole story. It is not even close, because when physicists looked harder and measured more carefully, the 3 neat quarks turned out to be only the faintest sketch of what is actually inside a proton. The 3 quarks are real, but they are like 3 swimmers you can name in the middle of a raging sea. They are there, but they are not most of what is there. Most of what is inside a proton is something far wilder, and to understand it, we have to meet the force that holds the quarks together, the strongest force in all of nature. We have met 3 of the 4 forces of nature on other nights. Gravity, the weakest of all. The electromagnetic force that runs the light and the nerves. And tonight, we meet the strongest one, the one that holds the quarks together inside the proton. It is called, plainly enough, the strong force, and it is strong almost beyond comparison. It is the force that binds the nucleus of every atom, that holds the protons and neutrons together against the electric repulsion that would otherwise blow them apart, that powers the sun and the stars. Inside the proton, it is the strong force that binds the 3 quarks, and it does so in a way unlike any other force we know. The strong force is carried by particles, the way the electromagnetic force is carried by photons. We met that idea on the night about electricity. 2 charges push on each other by trading photons back and forth. In the same way, the quarks are bound by trading particles between them, and these particles are called gluons. The name is a joke that stuck, because they are the glue that holds matter together. Gluons are the carriers of the strong force. They fly between the quarks, endlessly, binding them, gluing them into a proton. And here, the strong force does something no other force does, something that changes everything. With electricity, the photons that carry the force do not themselves carry charge. They are neutral messengers. But the gluons that carry the strong force do carry the strong force's version of charge, a property whimsically called color. This has nothing to do with real color, with red and green and blue as your eyes see them. It is just a name, a label for the kind of charge the strong force responds to, and physicists borrowed the word color because it comes in 3 kinds that combine in a way that reminded them of mixing light. The point is this: because the gluons themselves carry color, they do not just pass the force between quarks. They also pull on each other. They stick to each other. The glue is sticky to itself. And that one fact, that the carriers of the strong force also feel the strong force, is the reason the inside of a proton is a storm, and the reason a quark can never escape. Here is what that stickiness does. Remember, from the quark star night, the strange rule of the strong force. When quarks are close together, the force between them is gentle, and they move almost freely. But try to pull 2 quarks apart, and the force does not fade with distance, the way gravity or electricity would. It stays strong. In fact, it grows. Because the gluons between the quarks pull on each other, the force between 2 separating quarks gathers into a tight, narrow tube, a kind of taut string of glue, and the further you pull, the more energy you pour into that string. Pull hard enough, and you do not free a quark. Instead, the energy in the stretched string becomes so great that it snaps, and in the snapping, out of the pure energy, 2 brand new quarks are born, one at each broken end. You started trying to separate 2 quarks, and you ended up with 2 pairs. The quarks have sealed themselves away again. This is confinement. It is why no lone quark ever came out of all those collisions. You cannot isolate a quark. Pull one out, and the very act of pulling makes new ones to keep it company. The quarks are locked inside, forever, 3 to a proton, and the harder you try to free one, the more firmly the door shuts. That taut tube of glue between the quarks has a name. It is called a flux tube, or a string, and it is a real and measured thing, not just a picture. The force between 2 quarks, held apart, is roughly constant, like a stretched rubber band that pulls just as hard no matter how far you stretch it. That is utterly unlike gravity or electricity, which fade with distance. The strong force between separated quarks does not fade. The string just gets longer and stores more energy until it snaps. This is why the strong force is a prison with no distance to it. There is no running away. The further you go, the harder you are pulled back. And because the glue is so sticky to itself, physicists wondered something strange. If gluons pull on gluons, could you make a particle out of nothing but glue? A knot of pure, strong force, with no quarks in it at all, held together only by gluons gripping each other? Such a thing has a name. It is called a glue ball, and it may exist. Physicists have been hunting for glue balls for decades, sifting through the debris of collisions, looking for a particle made of pure binding, pure force, no matter at all. It is hard to be sure they have found one, because a glue ball would look much like other particles and could mix with them. But the theory says they should be there. A ball of glue, a particle woven from nothing but the strong force itself. It is one more strange resident of this small, roaring world. There is a last strange thing worth knowing, and it is that the emptiness inside a proton, and even the emptiness of ordinary space, is not truly empty for the strong force. The strong force fills the vacuum with a faint, permanent sea of quark and antiquark pairs, a background condensate, always there, even where there are no particles at all. When a quark moves through that sea, it drags on it, and that dragging adds to its effective mass and helps give the proton its weight. So even the nothing inside a proton is a kind of something, a quiet sea, humming with the strong force. There is, at this level of the world, no such thing as truly empty space. It is all quietly alive. It is worth pausing on how anyone worked out this strange behavior. The way the strong force fades up close and grips at a distance, because for a while it looked impossible. Every other force we knew got stronger as things came closer, and weaker as they moved apart. The strong force does the reverse, and no one could see how a force could possibly behave that way. It seemed to break the rules. Then, in 1973, 3 physicists cracked it. 2 of them, David Gross and his student Frank Wilczek, worked together. The third, David Politzer, found the same answer on his own at the same time. They showed, with the mathematics, that a force carried by particles that stick to each other, like the gluons, really can behave backward. It really can fade as things come close. They gave it the name we have been using: asymptotic freedom. The freedom the quarks feel when crushed close together. This was the key that turned the whole subject into a real, working theory, the theory we now call quantum chromodynamics. Once you knew the force faded up close, you could calculate things, at least in that regime, and the calculations matched the deep scattering experiments beautifully. It explained why the electrons that plunged deep into the proton found hard little points inside. Up that close, the quarks were nearly free, so they scattered the electrons cleanly, like free particles. It all fit. Gross, Politzer, and Wilczek shared the Nobel Prize for it, decades later, and it left us with the strange, lovely truth at the center of tonight. The quarks are most free when they are most crushed, and most imprisoned when they try to leave. The prison has no walls. It has only distance. And distance, for the strong force, is the one thing you can never cross. So now we can finally go inside and see what a proton really is. Forget the 3 neat marbles. Here is the truth. Inside a proton, the strong force is so intense and the gluons are so busy that the space is never empty and never still. The gluons fly between the quarks in enormous numbers, and because the strong force is so strong, it does something wild. Out of the sheer energy packed into that small space, particles are constantly being born and dying. Pairs of quarks and antiquarks flicker into existence, borrowed from the energy of the field, and vanish again a moment later. Gluons split into more gluons. The whole interior boils. It is not 3 quiet quarks in an empty bag. It is 3 quarks lost in a roaring sea of countless other quarks and antiquarks, appearing and disappearing, and gluons beyond counting, all churning together, held in a space unimaginably small. Physicists have names for the 2 layers of this. The 3 quarks we started with, the 2 ups and the down, are called the valence quarks. They are the ones that give the proton its identity, its charge, its lasting character. But swimming all around them is the sea quarks and the gluons, the boiling froth of particles that come and go. And at any given instant, the sea vastly outnumbers the 3 valence quarks. If you could take a snapshot inside a proton, you would not see 3 tidy dots. You would see a swarming, flickering crowd, a storm of particles too many and too fast to count, with 3 quarks somewhere in the mix that never quite vanish, riding the storm they create. And it is a storm precisely because the force is so strong. Remember the strange rule again, and now feel what it means inside the proton. When the quarks are very close, the force is weak, and they jostle almost freely, moving fast, nearly unbound. But as any quark drifts a little outward, the force ramps up and drags it back. So the quarks are forever rushing about inside their small prison, flying nearly free in the middle, hauled back sharply whenever they near the edge, never able to leave, never able to rest. The whole thing churns and seethes, a furious, ceaseless motion, bound into a shape smaller than almost anything you can name. A proton is not a particle in the way a marble is an object. A proton is a process. It is a storm that holds its shape. It is a knot of pure activity that has learned to stay tied. Let us go inside, in the mind, and simply look. It is a strange and beautiful place to visit on the way to sleep. Imagine shrinking down past your own cells, down into a single atom, past the far-drifting electrons, in toward the tiny nucleus, and in, at last, to a single proton, one small storm, and let us step inside it. It is not what you expected. It is not calm. It is not empty. It roars. Everywhere around you, particles flicker into being and vanish. Quarks appear and are gone. Antiquarks bloom and cancel. Gluons stream between everything, in numbers beyond counting, splitting and merging, a blizzard of them, filling all the space. There is no still center. There is no quiet corner. The 3 quarks you came to find are here, somewhere, but you can barely pick them out. They are lost in the crowd. They rush past, near the speed of light, flying almost free in the middle, and then the force catches them near the edge and hauls them back, and they wheel around and rush again. Nothing rests. Nothing holds still. And it is small. Unspeakably small. All of this, the whole roaring storm, is packed into a space 100,000 times narrower than the atom you fell through to get here. And yet inside it, there is so much going on, so much motion, so much energy, that it holds almost all the weight of the atom. A tiny room, and inside it, a hurricane that never ends. Look for the edge. There is not a hard wall. The storm simply fades near the boundary, the force gathering the quarks back whenever they try to leave. You could not tear one out. If you reached in and pulled a quark toward the edge, the force between it and the others would only grow, stretching into a taut string of pure energy until the string snapped and made 2 new quarks and sealed the wound. The storm will not let anything out. It will not let itself be undone. It has been raging like this, in this one proton, for nearly the whole age of the universe, and it will rage on, unchanged, long after tonight. Now step back out, up through the atom, back to your own size, back to the room. But carry the picture with you, because there is not one such storm. There are trillions upon trillions of them, all through your body, in every proton and neutron of every atom of you, all raging quietly, all holding their shape, all carrying their tiny share of your weight, right now, in the dark, while you lie here and breathe. And now we come to the most astonishing thing of the whole night, the fact that should make you feel the weight of your own body differently. It is about where the mass comes from, where your weight comes from. You would think the mass of a proton is just the mass of its 3 quarks added up. 3 quarks, each with some weight, stuck together, and the total is the proton. That is how it works with ordinary things. The mass of a bag of marbles is the mass of the marbles. But it is not how it works inside a proton, and the truth is stranger and more beautiful than almost anything in physics. The 3 quarks inside a proton are very light, astonishingly light. If you add up the mass of the 2 up quarks and the 1 down quark, their actual mass, the stuff of them, comes to only about 1% of the mass of the whole proton. 1%. So where is the other 99%? Where does almost all the weight of the proton, and therefore almost all the weight of you, actually come from, if not from the quarks? It comes from the storm. It comes from energy. Remember Einstein's most famous idea that energy and mass are 2 forms of the same thing, joined by the speed of light. Energy has mass, and inside the proton there is a tremendous amount of energy. The furious motion of the quarks, rushing about near the speed of light, the seething sea of particles flickering in and out, and above all, the enormous energy stored in the gluon field, in the strong force itself, in the strain of all that binding. All of that energy, by Einstein's rule, has mass. And when you add it up, that energy of the storm is where almost all the proton's mass comes from. The quarks provide the seed, 1%. The storm provides the rest. Sit with that, gently, because it changes what you are. Your body has weight. You feel it on the bed right now. And almost all of that weight is not made of any solid stuff at all. It is the energy of countless tiny storms, the strong force raging inside every proton and neutron of every atom of you, converted into mass by the deepest rule in physics. You are not, at bottom, made of little bits of matter. You are made, almost entirely, of bound energy, of force, of motion held in a shape. The solid, heavy feeling of your own body, the thing that presses into the mattress, is mostly the roar of the strong force, frozen into weight. When you feel how heavy you are tonight, you are feeling the storms inside your protons, 99 parts energy to 1 part stuff. You are far more a happening than a thing. There is a way to feel the enormity of that, if you like, though hold it lightly. Einstein's rule runs both ways. Energy has mass, which is why the storm gives the proton its weight. But mass, run the other way, is a vast store of energy. The rule says that even a tiny amount of mass holds a staggering amount of energy, because it is multiplied by the speed of light, squared, which is an enormous number. This is why the sun can shine for billions of years, by converting only a little of its mass. It is why a nuclear reactor can power a city from a small amount of fuel. And it means that the ordinary weight of your own body holds, locked inside it, an almost unimaginable amount of energy, sealed safely away in the binding of your protons, never released, just quietly being your weight. You are not only made of energy, you are, in a sense, a vast amount of energy, gathered into a calm and gentle shape, resting on a bed, doing nothing more dramatic than breathing. But it never comes out, and that is the mercy of it. The energy is locked in the binding, held there by the strong force, stable, patient, safe. It is not a fire waiting to burn. It is a stillness. The storm rages inside each proton, but the proton as a whole is calm and holds together and simply endures. So you carry this enormous locked energy through your whole life and never feel it and never spend it, and it costs you nothing. It is just the quiet weight of being made of matter, the price and the gift of having a body at all. There is a lovely twist to hold here about that other 1%, the small seed of mass that does come from the quarks themselves. Where do the quarks get their little mass? Not from the strong force. They get it from something else entirely, a different mechanism, one you may have heard of. They get it from the Higgs field, the thing the famous Higgs particle is a ripple in, discovered in 2012 at the Great Collider in Europe. The Higgs field fills all of space, and certain particles, as they move through it, are slowed by it, and that resistance shows up as mass. The quarks get their small mass this way, so does the electron. So the tiny seed of your mass, the 1%, comes from the Higgs. But the vast bulk of it, the 99%, comes from the strong force, from the storm, from bound energy. Two completely different sources, one small and one large, together making the weight of everything you are. The Higgs gets all the fame, but the strong force does almost all the work. Now, how big is this storm? How large is a proton? It is, of course, unimaginably small, and yet it does have a size, a definite width, and measuring it turns out to be surprisingly hard and even a little contentious. A proton is about 1 femtometer across, which is a millionth of a billionth of a meter. To picture how small that is, remember the atom as a stadium with a marble nucleus. The proton is one small part of that marble. It is roughly 100,000 times smaller than the whole atom. The storm we have been describing, the roaring sea of quarks and gluons, all of it is packed into a space so small that the number written out is almost meaningless to us. And yet it holds, we said, 99% of the weight of a body. The heaviness of you lives in specks 100,000 times smaller than the already tiny atom. And here is a genuine recent puzzle, one that unsettled physicists not long ago, and it shows how hard even this basic question is. For years, we measured the size of the proton in two different ways, and, much like the two measurements of the expanding universe, the two answers did not agree. One method used ordinary hydrogen, an electron orbiting a single proton, and measured the proton's size from the details of how the electron behaved. Another method, cleverer, replaced the electron with a heavier cousin called a muon, which orbits much closer to the proton and so feels its size more sharply. And when they measured the proton with the muon, they got a smaller answer. Noticeably smaller. The proton seemed to have two different sizes depending on how you looked at it, which should be impossible. This was called the proton radius puzzle, and for years it was a real and nagging mystery. Was our understanding of the proton wrong? Was there some new physics hiding in the disagreement? More careful measurements have since brought the two answers closer together, and most physicists now think the puzzle is largely resolved, with the smaller value likely correct and the earlier measurements slightly off. But it was a real reminder that even the size of a single proton, the most common particle in your body, is not a simple thing to pin down. and that nature guards her smallest details closely. And really, the very idea of the proton's size is a little strange when you think about it, because the proton has no hard edge at all. It is a storm, remember, that fades out toward its boundary. So when we say a proton is about 1 femtometer across, we do not mean it has a surface, like a marble. We mean that is roughly where the storm thins out, where the charge and the matter of it drop away to almost nothing. Measuring the size of a proton is a bit like measuring the size of a cloud, or a wave, or a person's reach. There is no exact line where it stops. There is only a region where it mostly is, and beyond which it mostly is not. So even asking how big a proton is turns out to be a subtler question than it sounds, because the proton is not a thing with an edge. It is a soft, fading region of intense activity, and we are asking where the activity dies away. No wonder it took such care to measure. There is a deeper puzzle inside the proton, though, one that is genuinely unsolved, and physicists find it more troubling than the question of size. It is about spin. Every proton spins, in a quantum sense. It has a fixed amount of a property called spin, a kind of built-in rotation. And this spin matters enormously. It is the reason magnets work, the reason certain medical scanners can see inside your body, the reason atoms line up in fields. The proton's spin is one of its most basic features. And here is the trouble. We do not know where it comes from. The simple picture says it should be easy. The proton is 3 quarks. Each quark has its own spin. Add up the spins of the 3 quarks, and you should get the spin of the proton. Clean and simple. So in the 1980s, physicists measured how much of the proton's spin comes from the spins of its quarks, and they expected the answer to be nearly all of it. Instead, they found that the quarks account for only a small fraction of the proton's spin, something like 1/3 at most, and early experiments suggested even less. The rest, the majority of the proton's spin, was simply missing. It was not in the quarks. This came to be called the proton spin crisis, and it landed hard because it meant we did not understand something as basic as why the proton spins the way it does. Where is the rest of the spin? It must be somewhere in the storm. Some of it, we now think, is carried by the gluons, which have their own spin. Some of it is carried by the actual orbital motion of the quarks and gluons swirling around inside, the way a planet has angular momentum from circling as well as from spinning. Adding all of these up, the quark spins, the gluon spins, and the swirling motion of the whole storm should give the proton's full spin. But measuring each piece is extraordinarily hard, and the accounting is not yet complete. We are still, today, trying to add up exactly where a proton's spin comes from. There is a whole large experiment being built, in part, to help answer it. It is a strange and humbling thing. The proton is the most common particle in the universe. There is one at the heart of every hydrogen atom, and hydrogen is most of the ordinary matter there is. And we cannot yet fully explain why it spins. The storm keeps some of its secrets still. And yet, for all that churning and mystery inside, the proton itself is one of the calmest, steadiest things in all of nature. Think about how strange that is. Inside, everything roars. Quarks fly at nearly the speed of light. Particles are born and die without pause. The strong force strains at its full ferocity. It is chaos, complete and ceaseless. And from the outside, the proton is perfectly serene. It holds one exact charge, always. It holds one exact mass, always, to a staggering number of decimal places. Every proton in the universe is identical to every other, down to the last detail, Whether it was made in the first second of time or in a star last week, the storm inside is wild beyond imagining, and the thing it makes is the most reliable, most identical, most unchanging object there is. There is something worth resting on in that, honestly. Great calm can come out of great motion. A thing can be all fury inside and all stillness outside. The proton does not hold its shape by being quiet within. It holds its shape by the perfect balance of an unquiet storm, every part rushing, every part pulling, and the whole, somehow, still. It is a little like a spinning top, which stands upright and steady only because it is spinning so fast. The proton stands, unchanging, for billions of years, precisely because inside it nothing ever rests. Its stillness is made of motion, and so, in a smaller way, is yours. Your body seems still, lying here, but it is held together, at the bottom, by storms that never stop. The calm of you rests on a foundation of ceaseless silent motion, all the way down. Here is a question that sounds almost childlike, and turns out to reach the deepest edges of physics. Does a proton last forever? You are made of protons. The protons in you are very old, made in the first few minutes after the beginning of the universe, or forged later in stars. They have lasted nearly 14 billion years already. But will they last forever? Is the proton truly eternal, or does it, someday, unimaginably far off, fall apart? This is not a settled question, and the answer matters more than you might think, because it touches whether ordinary matter itself is permanent. In our best tested theory, the proton is stable. It does not decay. There is nothing lighter for it to easily turn into while obeying all the rules, so it simply endures. But some deeper theories, the ones that try to unify the forces of nature into a single grander framework, the so-called grand unified theories, quietly predict that the proton is not perfectly stable after all. They suggest that, very rarely, unimaginably rarely, a proton might decay, might fall apart into lighter particles, a burst of energy where a piece of matter used to be. Not soon. The predicted lifetime is staggering. A proton, in these theories, might last on average far longer than the current age of the universe, not by a little, but by a factor with more than 20 zeros after it. Any single proton would almost certainly last far longer than the universe has so far existed. So how could you ever test that? You cannot watch one proton for that long, but you can use a trick. If any single proton is very, very unlikely to decay in a given year, then gather a truly enormous number of protons together and watch them all at once, and you might catch one, just one, in the act. So physicists built vast tanks, deep underground to shield them from cosmic rays, filled with thousands of tons of pure water, holding an unthinkable number of protons, and they surrounded them with sensitive detectors, and they watched and waited for years for a single proton anywhere in the tank to fall apart. The largest of these in Japan is called Super Kamiokande, a huge cavern of water lined with golden detectors sitting quietly under a mountain watching. And in all the years of watching, they have never once seen a proton decay. Not one. That silence is itself a result, and a valuable one. It tells us the proton lives at least a certain enormous span, longer than the simplest unified theories predicted, which has ruled some of those theories out. The proton is more stable than we can yet see the end of. As far as any experiment can tell, it may well be truly eternal. And that is a quietly comforting thought to hold in the dark. The protons in your body, the ones carrying almost all your weight, have lasted nearly the whole age of the universe, and will very likely last far, far beyond the death of the sun, beyond the burning out of the last stars, into spans of time the mind cannot hold. Whatever you are, at the level of your protons, you are made of some of the most durable things there are. Sit with the span of that for a moment, because it is a gentle thing to hold. A proton in your hand tonight has already existed for nearly 14 billion years. It watched the first stars ignite. It drifted through the birth and death of suns. It has been part of gas clouds and oceans and perhaps other living things long ago, before it came to be part of you. And it is nowhere near the end of its life. If the simplest hopeful theories are wrong, and the proton truly never decays, then the protons in you will outlast everything. They will outlast the sun. They will outlast the galaxy. They will drift on through the long, cold dark of the far future, unchanged, when the last star has burned out and the universe has gone quiet. You are, for a little while, the temporary home of some of the most permanent things in existence. They were here long before you. They will be here long after. And for now, tonight, they have gathered into you, and they hold you together patiently, as they have held together every atom they have ever been part of. There is a strange comfort in being made of such lasting things. Your thoughts are fleeting. Your day is gone by morning. Your whole life is a blink against the age of the protons that make you. And yet, you are built from them, from the enduring, from the nearly eternal. The impermanent you rests, entirely, on a foundation of the almost permanent. Whatever passes tonight, whatever the day was, the deep stuff of you goes on, steady and ancient, holding its shape in the dark. There is one more thing worth saying about the proton, and it is really the heart of why it is so strange and why we still cannot fully solve it. The proton is not a thing. It is a place. It is not an object you could ever hold or examine at rest, like a marble under glass. It is a churning region of space where the strong force is doing something so complicated that we cannot fully calculate it even now, even with all our theory. We have the equations of the strong force. We have known them for decades. They are called quantum chromodynamics, the theory of the color force, the gluons and the quarks. And they are, we believe, exactly correct. But they are so ferociously difficult to solve that, for something as complicated as a proton, no human being can solve them with pen and paper. The math is simply too hard. So how do we ever calculate anything about a proton at all? We use the largest computers we can build. Physicists take the equations of the strong force and they lay down an imaginary grid of points across a tiny cube of space, and they let the computer grind through the equations at every point over and over, simulating the storm inside the proton. This is called lattice quantum chromodynamics, and it is one of the great achievements of modern physics, and also a strange confession. To find out what a proton weighs, or how it behaves, we cannot reason it out. We have to build a virtual proton inside a supercomputer, run the storm, and measure the result. And when they do, when the great machines churn through the equations, out comes the right answer, the measured mass of the proton, 99% of its energy, matching reality. It is a triumph. We really do understand the proton in the sense that our equations, run on a computer, get it right. And it is humbling. We understand it only by simulating it, because the real thing is too complicated to hold in a human mind. So the proton keeps its dignity. It is the most common particle there is, sitting at the heart of every hydrogen atom, making up most of the ordinary matter in the universe and most of the weight of your own body. And it remains, in a real sense, beyond us. We cannot solve it by hand. We cannot fully account for its spin. We can barely agree on its size. We cannot say for certain whether it lives forever. The simplest, most ordinary building block of matter turns out to be a bottomless well of difficulty and wonder, a storm we can measure and simulate and marvel at, but never quite tame. And that is a lovely thing to rest against. The ordinary, looked at closely enough, is never ordinary at all. It is worth going back now to where the protons in you actually came from, because their story is nearly as old as the universe itself. In the first tiny fraction of a second after the beginning, there were no protons at all. It was too hot. As we saw on the quark star night, the universe was a searing soup of free quarks and gluons, the quark-gluon plasma, too hot for any of it to bind into protons. There were no atoms, no nuclei, no protons, no neutrons, just the storm, everywhere, filling all of space, uncontained. Then the universe expanded and cooled, and at about a millionth of a second in, it cooled just enough. The quarks came together, 3 by 3, and the gluons bound them, and the first protons and neutrons formed all across the universe at nearly the same moment. Every proton in your body was born in that instant, condensing out of the cooling storm, 1/100th of a blink after the beginning of everything. They are that old. They have been protons ever since. But there is a mystery folded into that moment, one of the deepest we have, and it is the reason you exist at all. When the quarks bound into protons, they should have been matched by an equal number of antiquarks binding into antiprotons, matter and antimatter, in perfect balance. And matter and antimatter, when they meet, annihilate completely, vanishing into light, as we saw on the electricity night. So by all rights, the early universe should have made equal amounts of both, and they should have wiped each other out entirely, leaving nothing but light, no protons, no matter, no you. But that is not what happened. Somehow, for reasons we still do not fully understand, there was a tiny imbalance. For every billion antiprotons, there were 1,000,000,001 protons. The billion pairs annihilated, filling the universe with light, and that one leftover proton in every billion survived. Everything you see, every star, every world, your entire body, is built from that tiny surplus, the one part in 1,000,000,000 of matter that had no antimatter to cancel it. Why the imbalance existed at all is one of the great unsolved questions in physics. But you are here because of it. You are made of the survivors. Think of what that means. Gently. Almost all the matter that the young universe made is gone, canceled, turned to light in the first moments. What remains, every proton in every star and world and body, is the thin residue that was left over, the one part in 1,000,000,000 that had no partner. You are not made of the main event. You are made of the leftover. The whole visible universe, all the galaxies, all the light of all the stars, is built from a faint surplus that the beginning almost, but not quite, balanced away. It is a humbling and rather beautiful thing to be made of. You are what the universe did not manage to erase. In the first few minutes, the newborn protons and neutrons did a little building. It was still hot enough, briefly, for some of them to stick together. So in those first minutes, some protons and neutrons fused into the nuclei of the lightest elements, mostly helium, along with traces of a few others. This is called primordial nucleosynthesis, the first cooking of the elements, and it happened everywhere in the universe in the first few minutes, and then stopped as the universe cooled too far to fuse anything more. That is why the universe, to this day, is about 3/4 hydrogen and about 1/4 helium, by mass. Those proportions were set in the first few minutes, and they still hold. A single lone proton, with nothing bound to it, is the nucleus of hydrogen, the simplest and most common atom there is. So most of the protons in the universe are still just that, bare hydrogen nuclei, unchanged since the first second, the oldest and simplest things there are. The strong force did not stop working after those first minutes. It has been building ever since in the hearts of stars. And this is where it becomes the maker of nearly everything. Remember that a proton weighs more than the sum of its quarks because of the energy of binding. Something similar, and even more useful, happens when protons and neutrons bind together into a nucleus. When the strong force pulls them together, it locks them into a lower energy state, more tightly bound, and the extra energy is released. And by Einstein's rule, the bound nucleus actually weighs slightly less than the separate pieces did. The missing mass has become energy and flown away as light and heat. This is called the mass defect, and it is the source of the greatest fires in the universe. It is why the sun shines. Deep in the sun's core, under crushing pressure and heat, protons are forced together, 4 of them at a time, through a series of steps, to build a nucleus of helium. And the helium nucleus weighs a little less than the 4 protons that made it. That tiny missing mass in every fusion becomes energy, streaming out of the sun as sunlight. The warmth on your face on a clear day is protons binding together in the heart of the sun, their lost mass turned to light, crossing the empty miles to reach you. The strong force, the same one raging inside every proton, is what lights the stars and has lit them for billions of years, one small mass defect at a time. And the heavier elements, the carbon and oxygen and iron, all the rest of you, were built the same way later, in bigger stars and their deaths, the strong force fusing protons and neutrons into ever larger nuclei, cooking the periodic table out of primordial hydrogen. Every element heavier than helium was assembled by the strong force in a star. The carbon in your cells, the oxygen in your breath, the iron in your blood, the calcium in your bones, all of it was bound together by the same force that holds a single proton, working at the hearts of stars over billions of years. So the strong force is not only what gives you your weight, it is what built the very atoms you are made of and what lights the star that keeps you alive. It is the quiet architect of the material world, working always at scales too small to see. There is a gentle symmetry in all of this worth resting on. The strong force binds the quarks into a proton, and almost all your weight is the energy of that binding. The strong force binds protons and neutrons into nuclei, and the energy released is what makes the stars shine and what forged your atoms. The same force, at 2 levels, gives you both your substance and your sunlight. It is the strongest force in nature, and it works entirely in the dark, inside spaces smaller than an atom, and you never feel it directly, and you are made of it, through and through. It is worth coming closer to home now, because the proton is not only an exotic thing in stars and colliders. It is in your hands, in your water, in your blood, doing quiet, everyday work, and once you see it there, the storm inside becomes personal. Start with the simplest fact. A single proton, all by itself, with 1 electron, is a hydrogen atom. Hydrogen is the most common element in the universe, and it is a huge part of you. Every molecule of water is 2 hydrogen atoms and 1 oxygen, and you are mostly water. So a great many of the protons in your body sit at the heart of hydrogen atoms, in the water of your cells, each one a tiny storm, holding its shape, carrying its weight. And a bare proton, A hydrogen atom that has lost its electron is something you know by another name. It is an acid. When chemists talk about how acidic something is, about pH, they are really talking about how many free protons are drifting in a liquid. An acid is a substance that lets go of protons. A base is one that soaks them up. The sharp taste of lemon, the sourness of vinegar, the acid in your stomach that digests your food, all of it is really about protons, bare protons, moving from one molecule to another. The pH of your blood is held in an extraordinarily narrow, carefully guarded range because it is the concentration of free protons, and your life depends on keeping it just so. Your body is, among other things, a delicate machine for managing protons, moving them, holding them, balancing them, moment by moment, so that everything works. The storm we traveled into is also the quiet chemistry of being alive. Even the way your cells make energy comes down to protons. Deep inside your cells are tiny structures that build your body's fuel, and the way they do it is to pump protons across a membrane, building up a crowd of them on one side, and then letting them flow back through, like water through a dam, and using that flow to power the machinery of life. Every cell in you runs, in part, on a flow of protons, a microscopic waterfall of them, turning a molecular wheel. So the proton is not only where your weight lives, it is how you breathe, how you digest, how your cells make the energy to keep you alive. The most exotic particle we have traveled into tonight is also one of the most intimate. It is doing your living for you right now, in numbers beyond counting. So the proton reaches from the first second of the universe, to the fusion in the sun, to the acid in your stomach, to the energy in every cell. It is ancient, and it is intimate. It is a storm too complex to solve, and it is the plainest chemistry there is. It is 1% stuff and 99% bound energy, and it is most of the weight of you. Hold all of that gently, and let us begin, now, to come back up, out of the storm, back through the scales, home to the body on the bed, which is, after all, only a vast and gentle gathering of these small storms, holding their shape together for a little while, as you. Before we come all the way home, there are a few more wonders about this small storm worth resting on, and the first is about its close cousin, the neutron. A proton and a neutron are almost twins. The proton is 2 up quarks and a down. The neutron is 2 downs and an up. They swap 1 quark, and they are nearly the same weight, nearly the same size, both storms of quarks and gluons. But they are not exactly the same weight. The neutron is very slightly heavier than the proton, just a touch. And that tiny difference, that faint extra heaviness of the neutron, is one of the most important small numbers in all of existence. Here is why. Because the neutron is a little heavier, a lone neutron, drifting free, is unstable. It will, after about 15 minutes on average, fall apart, turning into a proton and a couple of other particles. It decays, because there is a lighter thing for it to become. But the proton, being lighter, has nothing lighter to easily decay into, so it endures, stable, essentially forever, as we saw. Now imagine if the difference were reversed. Imagine if the proton were the heavier one. Then the proton would be the unstable one, and it would decay into the neutron. And a universe where protons decay into neutrons is a universe with no hydrogen, no water, no chemistry, no stars like our sun, no life. Everything would be different, and almost certainly lifeless. The fact that the neutron is heavier than the proton by less than 0.1% is one of the quiet reasons the universe can hold living things at all. And that tiny mass difference comes, in part from the small difference between the up and down quarks inside and from the electric energy of the storm. A hair of extra weight in the neutron, set at the dawn of time, and because of it, you are here. The second wonder is the mirror world. Every particle has an antiparticle, as we saw with the electron and its twin, the positron. The proton is no exception. There is an antiproton, exactly like a proton, but with the opposite charge, made of antiquarks instead of quarks. And we can make them. In the great colliders, out of pure energy, we create antiprotons, and we have even learned to slow them and trap them and combine them with anti-electrons to make whole atoms of antihydrogen, the mirror image of the simplest atom there is. We hold these antiatoms, a handful at a time, in magnetic traps for a little while, and study them gently to see if the mirror world behaves exactly like ours. So far, it seems to. But we handle them with enormous care, because if an antiproton ever touches an ordinary proton, they annihilate, both of them vanishing in a flash of pure energy, matter and antimatter canceling to light. It is the most complete destruction there is, and we can now bottle a whisper of it, a few atoms of a mirror universe, held in a magnetic bottle, kept carefully apart from everything else. And this brings back the great mystery of the beginning that we touched before. If every proton has a perfect antiproton twin, and the two annihilate whenever they meet, then why is there any matter at all? The early universe should have made them in equal numbers, and they should have wiped each other out completely. The fact that the antiprotons are gone and the protons remain, and that we have to work so hard just to make a handful of antimatter in a laboratory, is itself the evidence of that ancient imbalance. The universe chose matter by the faintest of margins, 1 part in a billion, and swept nearly all the antimatter away. We are the leftover. And when physicists trap those few atoms of antihydrogen and study them so carefully, part of what they are asking is exactly this. Why us? Why matter and not antimatter? What was different at the very beginning that let the protons survive and the antiprotons vanish? They do not yet know. It is one more open door, and a deep one, and it is written into the fact that you are made of matter and can hold antimatter only for the briefest moment, at arm's length, in a bottle made of fields. And the third wonder is that we have taken the storm apart, on purpose, and watched it come undone. Remember that inside a proton the quarks are confined, locked away, unable to escape. But we learned on the quark star night that if you crush or heat matter enough, the quarks can come loose, deconfined, into a free-flowing sea. We have done this in the laboratory, in the largest colliders, by smashing heavy nuclei together at nearly the speed of light. Physicists briefly heat matter to trillions of degrees, hotter than the center of any star, hot enough to melt the protons and neutrons themselves. For a fleeting instant, the quarks and gluons flow free, unconfined, a tiny drop of the quark-gluon plasma that filled the whole universe in its first millionth of a second. We have unleashed the storm from inside the proton, let it spill out and flow for a fraction of a second before it cools and the quarks lock themselves away again. We have seen, with our own machines, the state of matter that existed before there were protons at all, and it behaves, strangely, not like a gas, but like a nearly perfect liquid, the smoothest flowing fluid known. The inside of a proton, set free, flows like the most perfect liquid there is. So let us gather up the strangeness, gently, before we come home, because it is a soft thing to rest in. we set out to look inside a proton, expecting 3 small quarks. And we found a storm. We found that the 3 quarks are only a sketch, that they are lost in a churning sea of countless fleeting quarks and gluons. We found that almost none of the proton's mass comes from the quarks, that 99 parts in 100 are the pure energy of the strong force bound into weight. We found that we cannot say exactly where the proton's spin comes from, that we struggled even to measure its size, that we cannot solve it by hand and must simulate it in our largest machines, that we do not know for certain whether it lives forever, though it may, and that we do not fully understand why any protons survived the beginning at all, why there was that tiny surplus of matter that became everything. That is a remarkable amount of mystery for the most common particle in the universe. And we are not finished with it. New machines are being built right now to look inside the proton more clearly than ever, to make, in effect, a 3-dimensional map of the storm, to see how the quarks and gluons are arranged and how they move, to finally settle where the spin comes from. A great new instrument, an electron-ion collider, is being built for exactly this, to photograph the inside of a proton in a detail we have never had. So the story is not done. People alive right now are still trying to see clearly into the heart of the most ordinary thing there is. And every time they look closer, it turns out to be richer and stranger and more alive than the picture before. There is a lesson in that, quiet and worth keeping. The proton looked simple. 3 quarks, we said, and thought we were nearly done. And the closer we looked, the deeper it went, until the simplest brick of matter became a bottomless well of energy and motion and unanswered questions. The ordinary is never ordinary if you look closely enough. The plainest speck of you, examined to the bottom, opens into a storm as deep as anything in the cosmos. You do not have to travel to the edge of the universe to find wonder. It is inside every atom of your hand, raging quietly, holding you together, and it has been there all along. And it is worth saying, plainly, how much we do understand, because the mysteries can make it sound as if we are lost, and we are not. We have the exact equations of the strong force. We have known them for 50 years, and they have passed every test we can devise. We can predict, from those equations, the mass of the proton, and it comes out right. We can compute how the storm behaves at high energies, and it matches the colliders exactly. The theory of the strong force is one of the great triumphs of the human mind, as precise and as well tested as anything in science. The mysteries that remain, the spin, the size, the exact accounting of the storm, are not signs that we are wrong. They are signs that the proton is hard, genuinely hard, one of the hardest things in nature to calculate in full. We understand the rules perfectly. It is the game they produce that is so rich we are still learning to read it. So the proton stands, at the end of the night, as a kind of small miracle of the ordinary, fully governed by laws we know, and still, in its details, endlessly deep. It is the most common thing in the universe, and one of the most complex. It is the seat of your weight, and a bottomless well of physics. It has been studied for a century, and it still surprises us. And there is one inside every atom of you, more of them than there are stars in the sky, each a storm, each a wonder, holding you together, tonight, in the dark, asking nothing, as they always have. So let's come home now, slowly, back up out of the storm. Let the quarks and gluons blur back together. Let the roaring calm. Let the countless flickering particles settle into a haze, and the haze into a single small point, one proton holding its shape. From inside, it was a hurricane. From here, stepping back, it is only a quiet speck. Let it be a speck now. You do not have to hold the storm in your mind anymore. You saw it. You felt how deep it goes. Now let it fold back up, small and calm, and rest. There is no need to keep looking anymore tonight. It will go on without your looking, exactly as it always has, and exactly as it always will. It is unimaginably small, a millionth of a billionth of a meter, smaller than anything you will ever see. And inside it, the storm goes on, and will go on all night. But from out here, it is just a point of quiet matter, one of countless others, holding its place. Let us pull back, gently, and see where it sits. Come up a little, and the single proton is joined by others, and by neutrons, clustered together in a tiny knot. This is a nucleus, a handful of storms bound shoulder to shoulder by the same strong force into the core of an atom. And notice, gently, that the strong force is doing two things at once now, at two scales. Inside each proton, it binds the quarks into the storm, and between the protons and neutrons, it reaches out a little and binds them to each other, into the nucleus. The same force, holding the parts together, and then holding the wholes together, one level up. It is a bit like glue that first makes the bricks and then lays them into a wall. Without it, there would be no protons, and no nuclei, and no atoms, and no you. Still unimaginably small, still holding almost all the weight. A dozen storms, held in a knot smaller than you could ever see. Come up further, and around that nucleus, far out, a haze of electrons drifts, held there by the gentler electric force, kept at their distance, giving the atom its size. And now you have a whole atom, mostly empty space, a marble in a stadium, with the storms hidden at its heart. Almost all of it empty, almost all of its weight in that tiny central knot. Come up further still. The atoms join hands, sharing their electrons, linking into molecules, water, proteins, the long coiled threads that carry the pattern of you. Come up, and the molecules gather into cells, and the cells into tissues, into muscle and bone and blood and skin. Every one of them built on atoms, and every atom built around those tiny storms, the protons and neutrons holding almost all the weight, raging quietly, unfelt. Think of the layers of it, one inside the next, like a set of nested shells. The body, made of cells. The cells, made of molecules. The molecules, made of atoms. The atoms, mostly empty, with a tiny nucleus at the heart. The nucleus, a knot of protons and neutrons. And each proton and neutron, a storm of quarks and gluons, 1% stuff and 99% bound energy. All the way down, layer within layer, from the whole warm weight of you on the bed to the roaring dark inside a single proton. And all the way down, at every level, it holds. Nothing falls apart. Nothing lets go. The whole vast tower of you, from the body to the storm, stays standing, held by forces working quietly at every scale. And the number of the storms is beyond holding. There are more protons and neutrons in your body than there are grains of sand on every beach on Earth, more than there are stars in the whole observable universe. A number so large, it has no meaning to the mind. And every single one is a storm, complete, roaring, holding its shape. Trillions upon trillions upon trillions of them, all through you, all at once, all quiet, all faithful. You are not one storm. You are an ocean of them, past all counting, gathered into the shape of a person, lying here, breathing in the dark. and every one of them is calm on the outside, however wild within, so that the ocean of them, together, is calm too. The great quiet of your resting body is made of countless small storms, each one furious, each one perfectly contained, all of them together holding you gently still, and come up, at last, to the whole of you, to your body, lying here in the dark, on the bed, breathing. You are a vast and gentle gathering of these small storms. There are more protons in your body than there are stars in the observable universe. Far more, a number too large to hold in the mind, and every single one of them is a churning knot of quarks and gluons, 1% stuff and 99% bound energy, holding its shape, carrying its tiny share of your weight. Trillions upon trillions of them, all through you, each one a storm, all of them together, quiet, holding you. Feel the weight of your body on the bed now, and feel what it really is. It is not solid stuff, not at the bottom. It is the energy of countless storms, the strong force raging in every proton and neutron of you, made into mass, made into weight, made into the gentle heaviness that presses you into the mattress tonight. When you feel how heavy your arms are, how your body sinks into the bed, you are feeling the storms. You are feeling the strong force, the strongest thing there is, working quietly in numbers beyond counting, all through you, to make you a body with weight, lying here, in the dark. Let that change, just a little, how the weight feels tonight. It is not a burden. It is not dead matter pressing you down. It is energy. It is force. It is the strongest process in nature, gathered gently into your shape and holding it. The heaviness of your own limbs is the strong force, made calm, made yours. When you let your arm grow heavy and sink into the mattress, you are letting the storms settle, letting the weight of all that bound energy come to rest, and feel your breath moving in and out, slow and easy. The air you breathe is made of atoms too, each with its own tiny storms at the heart. You draw them in and let them go. A little of the universe passing through you and back out all night. There is nothing you have to do to it. It simply moves, the way the storms simply rage, the way the protons simply hold, all of it happening on its own, quietly, without you. So let the weight be gentle. Let it be energy at rest. Let your body grow heavy and calm on the bed, one great soft gathering of storms, all of them quiet now, all of them holding, all of them yours, for a little while, in the dark. So let the people we met tonight drift off now, one by one, the way you let go of a day. Democritus, guessing at the uncuttable atom 2,000 years too early. Rutherford, firing his little particles at gold foil and watching one bounce back and finding the nucleus. Chadwick, patiently cornering the neutron, the particle with no charge that hid so well. Gell-Mann and Zweig, seeing the order under the zoo, naming the quarks. Friedman, Kendall, and Taylor, firing electrons deep into the proton and glimpsing the hard points inside. Gross, Politzer, and Wilczek, working out how a force could fade up close and grip at a distance. Feynman, cautiously naming the parts inside partons before anyone was sure what they were. And all the ones still at it tonight, weighing the proton in their supercomputers, hunting its spin, building new machines to photograph the storm. You do not have to keep their names. Let them go. They did the work so the understanding would exist, not so that you would have to carry it. It lives out there now, in the equations, in the machines, in the world, whether or not you remember a word of it. And let the questions settle too, gently, because they were never yours to solve tonight. We do not know why matter survived the beginning. We do not know exactly where the proton's spin comes from. We do not know for certain if it lives forever. We cannot fully solve it, even now, even with our best machines. And even its size took a long argument to pin down. These are open questions, out in the world, held by people who love them, and not one of them needs anything from you tonight. Let them stay open. They are a soft place to lie down. A proton you cannot fully solve is a proton with wonders still in it, and there is one at the heart of every atom of you, keeping its secrets, holding you together in the dark. And feel, one more time, what you are made of. Not little marbles, storms, countless tiny storms, each one a knot of quarks and gluons, raging quietly in the dark, holding its shape, holding your weight. You are far more a happening than a thing. You are mostly energy, bound into form, for a little while, as a body, in a bed, in the dark. And the protons in you are old. They formed in the first 100th of a second after the beginning of the universe, condensing out of the cooling storm, nearly 14 billion years ago. They are among the oldest things there are. They were here before the stars. They were here before the earth. They will very likely be here long after the sun is gone, long after the last star burns out, into spans of time the mind cannot hold. For a little while, a handful of them have gathered into you, and when you are gone, they will drift on, unchanged, into whatever comes next. You are a brief arrangement of some of the most ancient and durable things in existence, and think gently of how far these small storms have carried you. They began in the first 100th of a second of the universe. They survived the great cancellation of matter and antimatter, the one proton in a billion that had no twin to destroy it. They drifted through the dark for billions of years. Some of them were pulled into stars and squeezed, and used to build heavier atoms, and scattered again when those stars died. And in time, a great gathering of them came together into a world, and into water, and into living things, and at last, into you. The storms in your body have been almost everywhere, and lasted almost forever, to arrive here, tonight, holding you together in the dark. And they ask nothing of you. That is the quiet grace of it. You do not have to feed the storms, or tend them, or even know they are there. They raged before you were born. They will rage while you sleep. They will rage on long after, when they have drifted out of you and into whatever comes next. You are not the owner of these storms. You are a guest of them for a little while. They gathered into your shape, and they will hold it faithfully for as long as you are here, and then they will let go, gently, and move on, unchanged, as ancient as ever. There is such peace in that, if you let there be. You do not have to hold yourself together. Something far older and far stronger than you is doing it, in every particle of you, without effort, without pause, without any need of your attention. The strongest force in nature is holding you, all the way down, and it has never once faltered, and it will not falter tonight. So there is nothing you need to do now, and nothing you need to hold. The storms will keep raging inside every proton of you, whether or not you think of them. The strong force will keep binding, keep holding you together, without a single thought from you. The protons will keep their shape, keep their weight, keep their ancient patience, all night long, asking nothing. It will all carry on exactly as it always has, whether you follow it or not. It will still be here in the morning, the storm, the strong force, the ancient protons, the open questions. And so will you, held together by the strongest force there is. You do not have to remember any of it. There is no test in the morning. No need to recall a valence quark from a gluon, or where the spin went, or why the neutron is heavier. Let the names go. Let the numbers go, the 99%, the femtometer, the trillions of years, all of it, out of your hands. It was never yours to carry. It was only something to listen to on the way down into sleep. All that is left, the only thing being asked of you now, is to lie here and be what you already are. A body made of storms, held together by the strongest force in nature, resting in the dark. Let the quarks go now. Let the gluons go. Let the storm blur back into a single quiet speck. Let the proton be a proton, whole and small, holding its shape. Let the nucleus be a nucleus. Let the atom be an atom. Let your body be a body, whole and warm, resting on the bed. Let the questions go too. Where the spin comes from. Whether the proton lives forever. Why any matter survived the beginning. Let them stay open, out in the world, where they are happy to wait. There is no answer due tonight. There is no test in the morning. And let the numbers go. The 99%, the 1 part in a billion, the trillions of years, the storms past counting. All of it, out of your hands. It was never yours to carry. So let your breathing slow. Let the storms rage on, quiet and unfelt, without your help. Let the strong force hold you, the way it always has. Let the ancient protons keep their shape, keep their patience, keep their weight, while you sleep. There is nothing to do but rest here, held together, whole, in a quiet, dark room, a gentle gathering of small storms, breathing in the dark. Feel it one more time, gently. The weight of you on the bed, which is energy at rest. The slow rise and fall of your breath, and under it all, past the body, past the cells, past the atoms, in every one of the countless tiny cores of you, the storms, raging quiet and unfelt, holding their shape, holding yours, the way they have since the first second of the universe. You do not have to feel them. You do not have to know them. They will hold you all the same. The room is dark. The bed is holding you. The storms are raging, everywhere inside you, quietly, the way they always have, and you do not have to help them, or understand them, or stay awake for any of it. You only have to lie here and be held by the strongest force there is, all the way down. Let yourself be heavy. Let yourself be calm. Let the storms rage on, quiet and faithful, and hold you through the night, the way they always have, and always will. So just rest now. It will all still be here, and so will you. Good night.